Okay, so this week we're looking at low level, the article by Costa's last name I'm not going to pronounce because I'll get it very, very wrong. Low level thinking in high level shading languages, which is a uh, follow-on, follow-up to a GDC talk from 2013. Yeah, is that the? Okay, I think I can get the PDF and look at it and I feel like I've actually gone through this presentation forever ago. Um, yeah, I think I watched this in like 2018, and it's some very nice tips on writing shaders that aren't going to hit the cases where the shader compiler barfs and produces some really yucky code. I'm not going to go through the whole thing.
I think I
Uh,
read this thing too, and the I think the one key takeaway is that a lot of this stuff is out of date, and the new GPUs just do the right thing, and you don't really need to worry about stuff as much anymore.
hmm. Well, are you talking about this article
I think the
or the original?
previous one, yeah.
I'm just gonna keep it open in case it gets referenced. Okay. Top three most influential presentations. Um, change the way I think about shader programming. And uh, yes, I mean quite literally, the first versions of programmable shaders are like you have like five or six assembly instructions to use because that's all that could fit in the shader model or the programmable hardware. It was very interesting. And then the language came a little bit, the HLSL like language. I don't know if it came after or if it meant was in addition to it, you because there was such a limited space, you could write it in assembly and get a lot out of it because the compiler was also just very young. Okay. Okay. So this is for people wanting to go deeper into shader programming. Um, yeah, 10 years is a lot of time. And the technology stack has also changed from the hardware to the compiler to the tasks we're trying to do. Um, so we're looking at RDNA 2, which is 3 or 4 years old. Because we have RDNA 3 now, and that came out like a year and a half ago. The 6.7 shader model is actually still pretty recent, I think. I'm I'm a Vulkan person, so like HLSL and shader model and DXC is all kind of, or DX, the compiler is all kind of foreign to me, but it's the fundamentals are still the same. Uh, so a big theme of the presentation was the compiler can't always optimize code good or code well. Inability to simplify operations to multiply add instructions, even if it could. Um, because here we have a add then multiply, which should be a mad instruction. The compiler, the previous presentation was issuing two instructions for it. Um, someone is typing. So, uh, wait, which compiler is it referring to?
DXE, I think, right?
Yeah. Okay. A bunch of multiplies. And so the compiler will not reorder things for you, which is very common. And the reason is probably that the ordering is important, but because of that, we're mixing a bunch of float and float threes, and that causes a whole bunch of churn. When if we could, multiply the floats together, uh, what? Where'd the oh there's the thing, and then multiply the float threes, we get a much better instruction count. So that's a gotcha that you'd think the compiler would just be like, oh, let me make this good for you, but no. Finish the derivations and implement features using the minimum number of operations needed. So the compiler won't do it for you. Uh,
It almost sounds like a SPUR-V disassembler would be handy.
it might. Uh, this is a whole other article with a bunch of things to.
This basically compiler can't do anything with floats.
Oh, dang. Well, this article seems the finisher derivation seems to imply that the compiler can't do your math for you, so you should try to do that and see if there's any simplifications you can make, which will make the thing just faster because then you'll be doing less math. So, and this will probably be another good article to read. Instruction modifiers are still a great way to get lots of operations for free. Saturate, multiply, and divide by 2 and 4, absolute value, negation are free. It's just this is a whole bunch of math that is just a single instruction, apparently.
Yep. So what language is this? This is the
RDNA,
or RDNA. Okay.
So the assembly is RDNA, and I think HLSL is the shader language. Yeah.
That's what I meant earlier. Like if you have HLSL on the left side and then what it compiles to on the right side, that sounds like it'd be nice to catch weird stuff like this.
I thought there was the shader playground did that.
They said this blog they're using Compiler Explorer. So
Oh,
Nice.
nice.
And I mean, so this is what goes into the driver, right? And what the
Yes.
driver actually produces could be completely different, right? So even though it's one instruction in this like assembly language, it could end up being more on the when it gets to down to the hardware. You don't know. So, but I guess it's a starting
Yes,
point.
but like this is RDNA 2, and it's not. It's pretty darn open. I mean, this is like x86. If there's a microcode going on, then I guess yeah, there might be something slightly different going on. But like,
Yeah, like in the old, like in that first or those old blog posts, it's all about like trying to do stuff with SIMD and all that. But it turns out nowadays it's like they don't even do SIMD anymore. It all gets converted into single register or whatever instructions. So it's hard, So like,
Scalar instructions.
yeah, I thought that's what it said. Like when it actually does the math, it's not doing SIMD anymore. It's actually doing like four
It-
different adds or four different multiplies. And because
Oh,
we
you
used
mean
to,
on the GPU?
yeah. And in the old days, you would try to like, if I was going to multiply four things that weren't actually related, I might actually put them into one vector and then do the operation together. But nowadays, it doesn't help. It doesn't actually add anything.
Yeah, the way old GPU instruction sets worked seems kind of weird, like vectors. But the new model is still, it's sort of like vectorized, but it's implicit. And it happens across a bunch of threads rather than being vectorized within one invocation, you know?
Yeah.
Anyway, so like I think the important point that the guy made early on is like measure, like test your performance and then try a bunch of different things and see what works. Because just because it's less instructions doesn't mean it's actually going to be faster.
Yeah, if you're using the original talk, where was it had a bunch of functions and kind of like a relative hierarchy, like cosine h, sine h, log 10. These are much costlier, even if they have one instruction. Well, I guess these would be in many individual instructions, but there could be because this is shader language, there could be instructions that are much costlier or have a lot of memory stallness to go on.
Sorry, I derailed.
What was that
No.
previous page you had pulled up where it's like, what are you doing with, what are you even doing writing shaders and stuff? Yeah, what's that from?
Gee,
Was, is
this is this article is pretty much a um modern update to this talk, or not this talk, sorry, this one.
Oh, okay. So yeah, I remember you said that. I just didn't know that that slide was from the talk. All right.
Yeah. So yeah, I'm flicking back and forth. Let me. I already. So yeah, this is the modern day stuff. Okay. Okay. So on input or output, it's applying modifiers. So this is describing the actual behavior of exp and log, so exponent and logarithm, and how it's implemented in terms of exponent exponent by 2. Or is that the same as pow?
It's 2 to the n.
Okay, yeah, 2 to the n.
So
Okay,
it was like bit shifting almost.
oh yeah, would be but
it
this one
allows
does.
float exponent as well.
Yeah, rather than calculating something explicit, exp using exp2 is just pre-multiplying by 144.
Well, I think that's a square root of 2, right?
Yeah,
If I remember my
it
numbers.
is.
Yeah.
Or I'm thinking of What's Euler's number?
Oh, that's like e raised to the pi or something.
Yeah, something. I don't know off the top hand. But yeah, these do the cheaper thing and then just multiply it because to the value that would be correct.
Never mind, I was wrong. I was thinking of another number. It's just 2.718. It's just e.
Okay, yeah. Compiler will calculate integer literal powers up to 4. So pow x3 is using a multiply. Any negative power will also use x exponent of the log. How of to the 1? Isn't this redundant? Taking anything to the first power is itself.
Yep,
Yeah.
you can just remove it, but I guess they don't check for that, or they didn't back whenever this was written.
Yeah, but also it's floating point operations, so probably they can't.
Yeah. Side note, a coworker was telling me about a time at a previous place, talking about shader compilers, and apparently, the compiler optimized to using a newer instruction that had less floating point precision issues, but some games were using that floating point imprecision in their tests, and so they started getting a bunch of visual artifacts, and they had to revert it, which I'm just like, oh yeah, floating point imprecision is no fun to deal with when you're actually trying to make things faster by using instructions that are more accurate and faster. But and you think, oh well, if it's more accurate, I can just apply it everywhere, and then everyone benefits. And it's like, no, you can't. So 1 over the square root of x. There's a reverse square root instruction, which that's good. Sign in inline conditionals. Sign also handle the case where x equals 0. Wait, what does the sign function do?
It just returns like positive
Plus or
1 or
minus
negative 1 or 0, depending on what the sign is.
Oh, okay. So it's what is the sign of x?
Yeah.
Okay.
So I guess what he's saying here is if you don't care about 0, then you can cut out an instruction.
That's
And if
nice.
you're just going to use that in 1 for something else, you can probably calculate it some other way too.
Ooh, ACOS. A lot of instructions. A lot of fuse multiply adds.
Yeah, aren't trigonometric like methods like some of the most expensive like operations that programs could do, like in general? Besides like fetching from like main memory.
Yeah, but the inverse trig
Actually,
is
not on
even
the
worse.
GPU.
Always profile to see if there's any gain, but it may be worth using approximations rather
Like
than
Taylor series.
I don't
I think
know.
that code there is probably Taylor series, implementing Taylor series. But I mean, if you could have a linear approximation or something like that where you don't really care that it's at exactly the right value.
Yeah, there's like the Hermite method, I think.
Or if I'm only going to calculate it between 1 and 0 or something, then you might be able to get a faster result.
Uh, yeah, this article, I'm trying to see if there's anything that sticks out, and it's like, wall of text. And then this is optimizing for GCN from 2014, and it's a bunch of slides. So there are places that talk about optimizing shaders specifically for inverse trigonometric functions. If you absolutely need these, but maybe there's faster ways to do it, like approximations. Ooh, quarter rate for sine, cos, log, and square root. RCP?
Reciprocal.
Okay. Okay. It's better to you roll your own matrix vector multiply function. Oh, geez. Um,
Oh, just because W is 1.
yeah. Hmm. Well, that's interesting. These reusing parts of a computation. It doesn't do it if the order is altered. Hmm. Is this a fused multiply add carry? I'm just gonna search it in the, oh, come on. In the reference here. Um, that's not telling me what it is, nor directly. Oh, it appears twice. That's it. Okay.
The AC stands for accumulate, by the way.
Well, what does the FM stand for then?
Fuse, multiply, and add.
Did you say the AC or the C?
Well, I think it should have two A's, but I guess it just looks cooler with one A.
Maybe it was
Okay.
called like fuse, multiply, accumulate.
Just try searching V underscore FMAC instead of the whole thing, and you'll find like more
Okay.
information.
Yeah.
Well, yeah, and accumulate just means the same thing as add, right? It's just a different way of writing it, I guess.
Yeah. Okay. Fuse, multiply, add of single precision votes, accumulate with destination. So
So you can see it just adds to the destination at the end.
oh, I get it. So it's multiplying the two numbers and writing and adding in the destination and and then adding the destination and storing it in the or getting the destination, storing it in the same place. Okay. Okay, yeah. That Mm. Okay, so I have loop directive.
It's like the opposite of an unroll directive. I'm not kidding. But yeah, it's pretty sad how ineffective it is.
Up to 50.
Would you typically want that? Just to keep the number of instructions count down, or?
Well, if the compiler unrolls too much, then it'll consume a lot of registers.
Right. Okay.
It's kind of like the no inline attribute in C++, where you can tell the compiler to never inline certain functions. That's kind of how I see it.
Yeah, because unrolling it, you think, oh, well, it doesn't have to do the check at the end to see, it doesn't have to do all the loop control logic, jump if blank, and it can just execute instructions. But if you are spilling your iCache on a CPU and then on GPU, I don't know what you would call it, but you have more memory pressure. They have to load all these instructions that then need to be executed. But if there's just a truckload of instructions because you've copied and pasted this 100 million times, then I mean it's kind of a space problem where you're trying to save time by using space like memory, but it doesn't end up saving any time because you need that space for other things than the instructions. If you just make the loop count unknown, it will keep it. I mean, makes sense because that's like how else would it know? I had the cursed thought of like an AI assisted compiler trying to guesstimate what would be the best, optimizations, and it might come up with the idea of just unrolling loops with no known size. So it might do something 3 times, it might do it 30, and there's only the AI would know which would happen.
Yeah, I think AMD's compiler only unrolls if it's known at compile time. And it does so super aggressively, like it'll blow up your register count,
Ooh.
which can be a problem. So sometimes you have to trick it by like putting the iteration count in a buffer or something, specifically to make it not unroll the loop.
You store the buffer size on a dedicated server that the shader compiler doesn't know about. So every time you invoke the shader compiler, it's left wondering, oh, well, I don't know how big this is. It's, some not known size. And
Does
only
that
when
mean?
Hmm?
Sorry, I thought you were done.
No, I'm making up silly things in my head.
I was just gonna say, like, does that mean like the ray marching algorithms that have like 300 iterations, like those can get unrolled, and then you have like 300 registers being used per like variable in there?
Yeah, it's kind of like that. So it sort of depends because what the compiler will do will try to hide the latency of like memory instructions. So if it unrolls a loop n times, then it'll try to put all the memory accesses, like all the loads up front next to each other, so they can all happen in parallel.
Oh, that couldn't work on a ray marcher because the ray marcher doesn't know what area it's accessing because it has dependent reads, right? Because you need to
Yeah.
know that you're how far you're going.
Yeah, so if you're dependent on the previous iteration, then you can't unroll.
Okay, that makes sense.
Okay. It used to throw an error when one tried to force a loop or a branch. When sampling a texture with UV coordinates calculated in the branch without specifying a MIP level. Sample a UV coordinate. You're not specifying a MIP level to sample from because okay, there. I wish this was just a bit wider so I didn't have to scroll to read the silly comments.
What I do sometimes is I right click inspect and then I make the width of the article like 100% so it fills the whole screen.
Inspect.
Or there's like tools in your browser where you could like hover over stuff and then it'll like show you. Yeah, that. Then you can like scroll to the top. Like, yeah, try to find like, because when you go to those, it'll highlight like what part of the page it's on. Yeah, that looks like it. Go up. You want to go to the highest one. That's like, yeah, try that one and then click on that. And then if you look in the right, it should say like width. You can like increase the width.
Max width.
Just do like a percentage, like 75% or something, or like maybe 80%.
80% larger.
It's like how much of the screen it's gonna take up. So if you do 80%, it'll take up like half.
That did not work. That what I
You
just
type
changed
you
there.
type percent in there. But yeah, this is what I do sometimes when I'm messing with articles that are like too narrow, is I just
Oh,
play with the percentages until like it gives me more real estate. Oh, you do
it's
percent, like a percent sign.
80%. Okay, come on, 80%.
Yeah, and then you can, it might change like which div you have to do it on, but it's kind of handy to do sometimes, like especially when the article is really narrow like this one.
Where is it?
It's
Didn't
kind of like
seem.
you gotta go back and forth between the right and the left, because the right is like the options for the layer, and then the left is like the layer. So now you made that one wider, and now you can see if it'll fix it if you do 80% there. Yes, there you go. So yeah, you can,
What? Did I just max width 80? Oh,
you can do like 100% too, because it's 80% relative to the previous one, I think.
just do 90%. Okay, well, it worked, so
Yeah, I do this all the time. It's so fucking annoying when they, I don't know if I was supposed to swear, but it's so annoying when they make it like for phones.
oh yeah, and it doesn't even work on a phone because you have this many characters and then it starts wrapping and it's like you can't read anything because it's wrapped so heavily and where were we?
So
Here.
new tool in your tool bag.
Well, I'll try to remember that. Um okay, so because we're doing stuff in a branch, it's doing a whole bunch of marking active threads, quad forcing for all pixels in the quad. Now activate the pixels in the quad wave that actually pass the test. Yeah. Um. Oh. So for the threads and pixels that don't follow the branch, UV coordinates are undefined. Shader can't calculate the UV derivatives to calculate the MIP level to use. Forces all the pixels in the quad on, makes them calculate the UV coordinates regardless of whether they follow branch, then take the branch as needed. So like This code says if data is greater than X, and the compiler is going to be sneaky and be like, actually, I'm going to move this code above the if statement because you have to, because of the, UV, the MIP level calculation. Is that what's yeah, and it sampled the texture only for pixels that pass the test. So yeah. Integer division is still really bad. 34 instructions for integer division. 24 instructions for unsigned integer division. Is this like article just going play by play from this one? Like, maybe. Because it just throws something at us randomly, or the next thing that it talks about is, completely unrelated to the previous one because just cube map sampling has an overhead. You should always look at the output of the compiler. So we have sample a texture and we get a float 4 out of it. And then index from a constant buffer. What?
Did you
Oh,
access vectors like that by the index? Like an
yeah,
array?
that makes sense. I had to realize that this is just saying can think of this as a array of 4 elements and we're gonna index in it. Okay. Um, so if you use the array syntax, this becomes a lot cleaner to read and works a lot better. So if you use floating point as an index, it got to be converted to an int. Convert EU32 to F32, which may require register allocation. So just use integer formats to begin with if you're doing that. Under the hood, all instructions are scalar. So we have a vec3 that we add a 1 to at the end to make to a vec4, then multiply it with m, and then get the vec3 out of it. Or convert it back to a vec3. So each register Vn holds a single float value. So all this is basically a lot of multiply adds because that's what matrix multiplication is. So I know on AMD hardware there's the vector general purpose register, which is the V registers. Scalar general purpose register, the S. VGPRs hold one float value for each thread of the wave, while SGPR holds one float value common to and accessible by all threads in a wave. So VGPRs are per wave, while SGPRs are shared. I was thinking like static, because like, you know, like a static variable in C and C++ is there's only one of it, whereas every time you know, like a local, no, never mind. It's a weird
Can they
analogy.
can the threads modify that scalar register, or is it constant?
Don't think it's constant. It'd be weird if it was.
It could be modified
Yeah.
using scalar instructions. The instructions prefix with an S.
So do you have like threading issues between like the waves, or I mean, I don't know if wait or the threads.
Well, the way it works is that there's one execution unit that executes 32 or 64 threads at once, but it only executes one instruction. If that makes sense. And the V instructions are like comparable to SIMD instructions, whereas
Yeah, I understand that. I wasn't sure if like they could like also modify the scalar, but I guess they would just read from it. They would never write to it.
well, you can write to the scalar registers, but that's
But
done
you
with
couldn't
scalar
do it.
instructions.
You couldn't do it like during the process you're talking about, where like it's executing multiple like like it's doing the SIMD operations. Like, you know what I mean? Like while it's doing a SIMD operation, it's executing like like a bunch of threads at once. Those threads in the SIMD operation can't modify the scalar. It's only like it has to be synchronized or something like that, right? Or
Isn't it that there is one instruction stream? So like all 64 of these threads they're running the same instruction, and the compiler won't emit instructions. Like they're not threads like CPUs where you have multiple things operating in at different times. It's like, no, you have one instruction which has each thread,
yeah, I
each
understand.
lane write to its own VGPR, and then you have another instruction which like
So
loads
I
a
guess
constant value to the SGPR.
what if the instruction is like store your value in the scalar? Then you
Well,
have
there is no instruction that does that. The only
so
instructions that can write to an SGPR are scalar instructions, which are, you know, I guess it wouldn't make sense to have a vector instruction that writes to an SGPR.
yeah, that's what I was asking. So it's if you ever modify the scalar register, it's basically like it almost like an atomic I don't want to say atomic operation because that's threading, but it can't work within like that SIMD like instruction. Like it would basically like waste like however many registers of instructions there are, because you have to have one the executor would only have one instruction to write to the scalar, instead of like running all the instead of doing like its full capacity, right? Like it'd be like instead of it running like a bunch of SIMD instructions, and then it would have to do a normal instruction to update the scalar register.
Right.
I mean,
I think it's still like, imagine this scenario, like I have a counter in my loop, right? And I'm going to decrement the counter, but the counter is the same for every thread. But still, each thread has to, I mean, the counter has to get incremented, right? So even though it's like an instruction that does exactly the same thing on every thread, it still has to happen on every thread.
Okay,
Right?
so
So
so if I can rephrase it in a way to see if I understand this right,
yeah,
you have a loop, and let's just say the loop's like adding a bunch of stuff. So when the executor is running inside the loop, it's doing SIMD instructions on every thread that is essentially representing every thread. So like all these SIMD instructions are adding, so it's like 16 adds per like iteration per instruction inside the loop. But then once it has to increment the counter, it doesn't do SIMD anymore. It just does like a normal instruction to increment the counter inside the scaler.
Yep.
Yeah.
Yep.
Okay, that makes sense.
I was thinking if it like there's an ALU associated with each of these lanes, and then there's just whenever you do an SGPR instruction, all of the vector ALUs just sit idle for that instruction because there's
Well,
just
you
nothing to
can
do.
overlap.
Well,
Like there's separate ALUs, so you can
Uh-oh, you refresh
Sure.
the page.
you can
Oh.
issue a vector instruction followed by a scalar instruction, and they can operate, they execute in parallel.
So how does the parallelization work? Is that something that you have to bake into your instruction stream, or does it have an out of order kind of?
It's just
Decoder.
multiple pipelines instructions can execute in.
Okay, but it's like, so I guess but the decoder can you can decode multiple instructions in one clock or whatever.
Well, no, it decodes one instruction per clock, but well, sort of depends, but yeah, you can think of it as decoding one instruction per clock.
It sounds really
But the
similar to how
instruction-
this. Oh, sorry, I thought you were done.
Oh, I was just gonna say instructions take multiple clocks to complete.
Okay.
It
multiple
sounds
cycles.
very similar to how CPU SIMD works, where CPU SIMD has like throughput and stuff. And like, from what I understand, like the CPU instruction, I might not fully understand this, but this is how I understand it. When you do a SIMD instruction on the CPU, it basically like whatever execution pipeline is used, like the float execution pipeline or the arithmetic execution pipeline, it basically is just like telling it like it's just filling that pipeline really, and like the other pipelines might sit idle and stuff.
But like
Yeah.
on an x86, it actually decodes multiple instructions per clock. So
It's really weird on x86 because on x86 like you can have like a swizzle instruction and then you can have like a bunch of float operation instructions, and since the swizzle is like an arithmetic logical thing, those are basically free because your float operation pipeline is going to be full most of the time. So swizzles are actually not that bad
Mhm.
because
Yeah.
if you have to think in terms of like execution pipelines, which I don't know how it works on the GPU, which I'd be interested to look into that, but that's how it works
Pretty
on CPU.
similar.
Yeah,
There's
like
sorry.
I get one different thing. What I'm guessing is different on a CPU versus GPU is that the CPUs have register renaming, right? And so even though you may be using the same register name in your assembly code, when it actually runs, it might actually be, automatically renamed into multiple registers. Like I think on x86, even though it has 16 registers, there's actually like 192 registers in hardware, right? And if some operation gets delayed, then it can,
Yeah, they can detect dependencies automatically, and the GPU hardware does not have that sort of complexity.
I didn't know about the register renaming. That's really interesting. I knew AVX 512 has like 16 or 32 registers, but that's like 32 512-bit registers, so it's like actually a ton of memory. But I gotta look into the register
Yeah,
renaming.
so the
That's really
renaming
cool.
may only be for the scalar registers like RAX, and I'm not sure if it does it for SIMD.
Yeah, I'm gonna look into that.
well, more sRGP, VRGB, VGPR, SGPR. It's saying that a scalar load is cheap and a vector load is expensive, and the compiler will do a scalar load if it knows or is certain it can, but if it can't, it's gonna do a vector load, and even if the value might actually be the same, it's going to be a lot more expensive.
That makes sense.
That's a fat instruction.
That's because it is a type buffer load, which is sad.
So type buffer is an instruction you never want to have in your code if you can help it. Is that what I'm hearing?
No, it's not that it's bad for performance necessarily, but it's just it's like using a textual buffer in Vulkan.
Ah,
It just does the format conversion automatically.
there's the baggage. Like what you were saying earlier, scalar unit doesn't support all operations. Can't do floating point math or multiplication with it. Can do integer multiplication, and integer division is even worse. So for SGPRs, so yeah,
I always heard GPUs didn't have good support of integers,
that is also what I've heard.
so that surprises me. I heard that GPUs fake integers, basically. I don't know if that's true, but that's kind of like,
No, well, what this is saying is that um never mind.
It's saying avoid division on integers, I think is the main
Yeah,
thing. Yeah.
yeah. Oh, here's a big paragraph of text. Okay. Okay.
how
There's a
old is this paragraph? Is this article, by the way? Is it new?
2023.
Okay.
Okay, that's just the thing. In general, I found that most of the things mentioned in the follow-up presentation still hold up. So let's look at what's changed. GPUs have gotten very wide. ALU capacity has increased. Memory, latency / bandwidth, and fixed function units haven't scaled by the same amount. I mean, you can't have everything. Gigaflops per second to memory bandwidth ratio has increased. Oh goodness, the 408070s. Yeah, that article's from a while ago. So the ratio of ALU to memory bandwidth was 10 and is now 76 for a RX 7600. I'm gonna side note and say I find it hilarious that the Radeon 4870 and the Radeon 7600 make it look like there's, a couple of thousand of product numbers in between it. But no, what happened was the product numbers cut off the last digit, went to like the 4080 and the 580 and have since gone back to 4,000 digit of 4-digit number product codes. And so there's like a weird timeline in terms of the product names in between these two GPUs. Okay, so a ratio of 10 to 76, and the text ALU to texture rate 40 to 65. So fixed function will struggle to fill the GPU work even more because the memory bandwidth has not increased by this at the same rate as the fixed function and ALU capabilities. So we got DX12 coming in like 2015. Way more control, how you set up and feed data to shaders. And there's more things peripheral to shader authoring. descriptors and binding resources to shaders. DX12 makes interaction with shaders. There's root signatures and a choice of root parameter types more explicit. Most efficient way to pass data to the shader is directly in the root signature. The most expensive via doubled indirection via descriptor table. So you got lots of flexibility in how you pass things to shaders, unlike DX11, which was more, you had a couple of ways and the GPU the driver just did it for you. More expensive if due to a high number of root parameters, part of the root signature has to be stored in memory. Yeah. My understanding of the root signature and root parameters is like you get a fixed number of basically static storage for the shader execution, and so when you execute the shader, it loads all of those things statically, and then if you have to, if you have to do a memory read to get the actual location of the descriptors, then that slows things down. And if the size of the static section is just massive, then you have to do another memory road. It's like it's register spilling in a nutshell, isn't it? Yeah, knowing these things is important. So barriers and resource transitions can also hurt.
One thing that's nice about I forgot the compiler, but I know it's LLVM, but I think you can detect register spills if you're using SIMD. Like there's a way, there's like a compiler optimization log, and it'll tell you like if there were spills. That's pretty cool.
Yeah, I seem to remember hearing about that.
Yeah, I think I mentioned it here last time.
Yeah. And just being able to know when your vectorization works or doesn't work, or how well it works, is just useful to know. GPUs will overlap shader work from different draw calls and dispatches. They don't have dependencies. And now we have ways to make that overlap more explicit. So if you have a bunch of complementary workloads,
So is
you can
this like
have
doing multiple draw calls with the same shader on different things?
No, I think it's more saying that the driver can do more work at the same time, without you having to like if you have a properly resource barriered work graph, or draw shader graph,
Render graph, I think.
render graph, thank you. I mean the APIs make you explicitly fill out all that information, and you can't have shaders that read and write to the same, you usually can't have shaders that read and write to the same memory locations. I mean, that's just,
Oh, it said complementary work, so I just assumed it was like the same work, but just different draws.
yeah, okay, maybe I just misunderstood you. Because my understanding was like different draw calls, not different, like different draw calls that don't interact.
Oh, I when it says the complementary workloads, I assumed it was like the same shader. Because then it could say like, yeah, these are doing the same thing. Like, how would it know what complementary workloads are? Is it just like, is it just kind of like, oh yeah, uh, there's a read coming up in these two things, so let's put them together. Like, or am I misunderstanding this?
I think like if you have uh a draw call to, like, if you're doing shadow map computation and SSAO computation, you can do those independently, and then the GPU can actually work on those at the same time and utilize utilize the hardware more effectively.
Okay, I think I misunderstood what they meant.
But-
I kind of thought it kind of sounded like they were doing like when we were talking about the vectorization earlier, it kind of sounded like it was mixing like multiple draws in the same vectorization. So that's kind of what, but honestly, now that I think about it, it doesn't make much sense to do that. So I think I just misunderstood it.
Yeah. I know the word async compute has been. I heard so much about it when I was watching more of the general audience stuff, and it seems to be it's a thing and it's good, but there's a certain amount of buzzwordiness around it that makes it hard to look up the actual technical details. But I also haven't been looking into that for a while, so I wouldn't say it's a definitive statement about today. Yeah, always profile. Hmm. Oh God. Material complexity and lighting model complexity has absolutely increased. More texture reads and more ALU, more divergence. And ray tracing is more like all the divergence, at least in real world scenes. Multiple ways to address it, which have different contexts and things about them. Uh, hmm. Okay, yeah. And then getting to, we've been doing a lot of individual instruction optimization discussion. Now we get to memory and memory latency. Occupancy can be important as an indication to how well the GPU can hide memory latency. So occupancy refers to the amount of waves the SIMD can have in flight in case of wave instruction gets blocked by a memory read. It's affected by the number of VGPRs. So the advice in the original presentation applies as far as like if you follow the advice, it'll improve the occupancy. But it's not the only measure of latency or how well latency hiding. So the compiler may be trying to put instructions between the read and the use of the memory. So we have a sample, we have some multiplication, and then the actual use of the sample here. And here we have the actual instructions in between it. Uh,
Wait, why does that one have a block? Is it because of the read?
yeah, so these three lines are the same except the second and third line were switched. So we have vec, we have a sample and then we have a usage of that. Whereas up here we have the sample in the first line, but the usage is on the third line. So the compiler has all the code for the second line, it can shove in the middle. Whereas in here, it can't do that, so it has to block until it's ready, which, might be a stall. There's just
Oh, that's really bizarre. So you got when you do texture reads, like you might want to order your instructions so that the action when it's actually used, it's like later.
yeah. I feel like for me personally, this feels like this is something a compiler would be better at handling than I would, at least at a scale. But I'm also not a shader compiler author, and I
I
don't know the
rem
considerations for reordering.
the compiler will try to do that as best it can.
Okay.
I remember I was watching a presentation. It's kind of famous. It's the data-oriented design one by Mike Acton,
Yeah.
and he said something like, "Do everything, even things that like when you're like, why can't the compiler do that? Do it anyways." But I think when his background, like I think he was doing games like when like C++ compilers weren't so great and they still had to do stuff in assembly because the compilers were not there yet. It might be a similar thing where the GPU compilers are just not like there yet. I don't know.
I hear his talk, and then I see people trying to understand what he's saying, and I see a lot of misunderstanding of what he was saying and a lot of wasted effort. You
Yeah,
know,
it took me a long
profile,
time.
profile. It's
Well,
the
I
main
think he says
thing.
that. I think he says that in the presentation. He's like, "When's the last time you profiled?"
Yeah, it's been a
Not
while since I've
yesterday,
seen that
recently.
talk, so
It's kind of I've watched it so many times because it's so hard to like understand. It's like you said, it's really hard to understand what he says, and you can like misinterpret a lot of what he says. So I have it like I've listened to it every like couple of years or maybe like something like that, and so now I have like random parts of it just like stitched in my brain.
uh yeah. I mean, yeah, there's a lot of things in that talk that are applicable in a lot of domains. Or there's a lot of good kernels of wisdom.
That you could just take the wrong way though.
Yeah, that's absolutely true. But like you can lead a horse to water, you can't make it drink is a classic saying for a lot of things.
Well, I think if you just see that presentation like in a void, it's like how are you supposed to know that like he's talking about like SIMD and stuff? And yeah, I don't know.
Yeah.
Well, I think the important thing, and which they already talked about in this talk, or this paper here, is that you know, you want to worry about the memory caches, right? And you want to keep stuff that you're going to be using together in memory, right? So
And
it's,
you want to
you want to have like an array or a structure of arrays instead of an array of structures, stuff like that.
for GPUs, it's a kind of a different ball game because I'm like, how much of GPUs are doing this structure of array versus array of structures thing? Like, I'm not thinking about that as much. What you're doing in GPU land much more often is going, hey, why are we loading 4 floats per lane? What if we compress like our UV core, not our UV cores. What if we compress our normal map to using like octahedral encoding because then we can use a quarter or, like a
Yep.
third as much memory. And now you've saved a bunch of bandwidth and made everything a lot faster. And the cost of reading and writing is reduced even though you're doing a bunch more ALU instructions because
Right.
the ALU is sitting idle anyways.
Or just like if I have some algorithm that I'm are doing, then I just need the stuff for that algorithm in it, preferably all in the same texture.
Yeah. Instead of like
And
4
all the other
textures.
stuff can be in some other texture, whatever.
Mm-hmm.
It sounds like on GPU stuff is structure of arrays by default. You just don't see it because it's like implicitly done because your code's
Yes.
ran in a register.
You still need to think about memory access and structure layout on the GPU. Like if you have a path that renders a shadow map, for example, if your vertices are not stored as a structure of arrays, then it will be slower because you load unnecessary data.
Oh yeah, vertex interleaved vertexes buffers versus where you have like the buffers, the positions, the UVs, and like the normals are all three separate sections of the vertex buffer. That totally is a SOA versus AOS.
Or like if
Yeah.
you're just
Same,
memory bound in
same with
general,
like
you have to think about it.
depth pre-pass versus like G buffers and stuff too. It's kind of like that.
Yeah.
Like
Well,
it
there's
matters a lot
structure
on the
of
GPU. So
the structure of arrays of structures.
Yeah, you could have that. I mean,
Well,
I think
you're already inside a structure of arrays, so you can make your. I don't know. It's
No, that
it's
actually is totally correct, right?
Yeah.
A structure of array of structures, as long as the like each structure fits in a cache line or something, you know.
yeah, you
Yeah.
can do that.
Yeah.
I think there's also the idea of hot cold splitting, which is kind of related to the SOA concept. If you have stuff that's often used together, then you want to split off that data in a separate piece of memory or buffer
I remember when I did
to
did like
optimize.
I did a fluid sim recently, and the biggest performance gains were almost all memory. Aside from like multi-threading it, like they were almost all memory stuff. Like it wasn't like changing the algorithm around, like you got a small gain, but then like localizing the memory better, it would just like double or triple the FPS.
I mean, there are algorithms too, which are like what is that called? There's like a multi-resolution version of like the pressure solver that's like super fast. I think it's called multi-grid. So that's kind of like map kind of idea.
I was considering doing that, but I didn't get that far. But I'm pretty sure that there's a guy on Twitter. His name's Grant Cott. He's got like an ocean simulator that runs on his computer. It's like an insane amount of water, and he's got like ships in it and stuff. And he probably does something like that.
I'm sorry, but I was just imagining my computer case is a horizontal case where like the motherboard's laying flat. And I'm just like, well, if the sides of the case are solid enough to hold water, I could simulate an ocean on my computer too, pouring like a bucket of water on it,
You could do.
putting a
Have you
little
seen the
rubber
aquarium
ducks and
computers?
oh yeah,
You
like
can do
if
that.
oh
That's cool because you get cooling too, right? In addition to having nice
yeah.
fish to look at.
Well, you can also submerge computers in like mineral oil, but you
That's how
can't
they
put
work.
fish in that. The
Well,
fish
what
will
they
die.
do, I think the mineral oil sinks to the bottom. So you do mineral oil and then you do water on top, and then the fish just separate naturally. I don't know for
have no
sure. I mean,
clue. My
but then
my
you'd have to deal with.
expectation is like two separate tanks where the internal one it's all glass, so the mineral oil is the next to the computer, and there's just a separate tank on the outside where the fish are. But
You also probably want to separate it just because you don't want like fish shitting in your GPU fans.
that too. Um, but to finish out this article, because we've been going for a while, wave intrinsics are a thing. Subgroups are operations, or what they call it in the Vulkan world. And they're pretty awesome. And they make a lot of things pretty fast if you know how to use them. And that's cool. But I kind of want to skip over it because there's just a lot to say about it. To summarize, it's less about saving odd ALU instruction, more about understanding the tools platform you're working with and working with a compiler instead of blindly relying on it. Compiler technology has evolved, but it's still not great. We need to work with it. Don't make assumptions about what the compiler will do. Read and understand the compiler's output when you have the opportunity to do so. Don't always have to worry about extra instructions. That's a good takeaway. Just because the output has like 38 instructions doesn't necessarily mean it's a bad thing. Um, batching operations by type, not using integer division, or too much injurious trigonometry. Understand the bottlenecks in each case. Make sure the GPU resource is not wasted. Always profile to see the impact. The result may surprise you. That should have been the title. Like, the result may surprise you. In like clickbaity voice.
I was listening to a guy, I think he was from SG14, which is like the game dev for the
And
C++
low latency.
committee.
Low latency
And
game dev subgroup.
yeah, he said something like he put a print statement in the middle of like some code he was testing while trying to get better performance, and it made the code faster because the compiler like did some weird optimization to like never run that section of code. And he was thinking of like just leaving it in there because it made the code faster.
Yeah, so
And-
I saw this. I don't know I don't have the link for it right now, but like on Linux, like your like environment gets copied onto your stack whenever you start your process, right? And that actually moves the where all the stuff on the stack is stored. And if it depending on where you are in like a page boundary or a cache line boundary, it can actually like destroy your performance by just changing the environment. So like something outside of your executable can have, slow you down by 40% or something.
There is a talk about that Google gave,
Yeah.
and then they
it was a keynote from 2020 C++ Con. I'm trying to think of the name of that talk.
yeah, and
Sorry.
they showed a tool called Layout Randomizer or something like that. It randomizes the layout of your program, including things like the environment.
Yep.
But I think it's not
Yeah,
maintained
I've heard of
anymore.
that. Yeah. Is that like supposed to counteract the effects of like environment?
Oh
Right,
yeah,
or
yeah. It's
actually,
supposed to counter that, or it's supposed to help you profile, I guess.
Performance matters, Emery Burger. That's the talk I'm thinking of.
Yeah.
Um,
The only thing I remember from that talk is like the just the layout of the memory can affect performance in some random way.
is this it?
You have to click
Yeah, I
more
think
page
that's it. Yeah.
at the
Well,
bottom.
I know the name of the talk. So
There's a button at the bottom, and GitHub doesn't show the whole presentation. More pages.
oh
Yeah, this is the
oh
one. Yeah.
okay. So the thing I'm just
So
gonna
this
look
one
up
is actually talking about like what how you figure out asynchronous issues, right?
async
Like if you're doing
bugs.
running a bunch of stuff in parallel, and like how do you measure the performance of your whole parallel, or how do you profile a bunch of different threads all running at the same time? And they put in delays all over the place to try to
Well,
figure it out.
to be more specific, it wasn't random delays. It was if you have a system oh God, this is a lot of Simpsons pictures. I don't know why. I just want like a better slide deck. Anyhow, the way to measure the relative performance speed up is to slow everything down by the same ratio. And the point of it is to find where the actual bottleneck is rather than just a thinking that because this part of the pipeline is taking X amount of time, therefore it is the bottleneck. It's like, no, the only way to quantify where the bottleneck is to make everything slower in comparison. Which if you're like doing operations between servers versus on a single computer, I'm like, oh, that can make a lot of sense because there's a lot more moving parts when you're doing like, in the presentation, I think he used some sort of example example app that users would upload images and then you'd have a big pipeline run to compress and analyze and do all that stuff. So is this better slide deck? Wait, I did close the GitHub one. Maybe I should have just used that.
I think we should stop recording.
Yeah, we should restart recordings. Yes, definitely.